Please wait
Please
5
wait
minutes.
5 minutes.
Okay, good evening all. Let's wait 2 to 3 minutes more. People may be join. So here is the my detail. We have already discussed first assignment based on the solar irradiation. Now we will discuss the second assignment, which is purely dependent on the semiconductor. Okay. Okay, so let me project first question to you. See, what is the first question? Are you able to see my slides? Okay, thank you for your response. And my voice is also audible to you. Okay, thank you. So let's discuss the first question. What is the question? In indirect bandgap semiconductor, a transition between conduction band and valence band result in. You can ask any question, any doubts in the chat box also, or you can unmute yourself and can ask. Okay, so this is the question. Do you know what direct or indirect bandgap semiconductor? Tell me yes or no in the chat box. Then we will discuss about the direct and indirect, then we'll discuss this question answer. Please response. Do you know direct and indirect band gap semiconductors? What are the direct and what are the indirect band gap semiconductor? Do you know? If not, then we will discuss. Okay, sir. Okay, I will explain to all direct and indirect semiconductor. So, in the semiconductor means there is a two levels, which is valence band. One is valence, one is conduction band. Valence band is below and conduction band is top of. This is K versus E. So EK diagram, in EK diagram, conduction band edge, this is called like parabolic in structure. Parabolic in nature. Why? Free electron is given by the energy is like parabola. So this is the maxima, this is minima. Agree? This is conduction band and this is valence. When any material, any semiconductor, upon incident the light, absorb this photon and jump electron and hole phase, electron goes up in the conduction band. This is known as absorption. Transition from valence band to conduction band of electron will contribute in the electricity in solar cell application. So this is important, direct and indirect. Let me explain what is direct, what is indirect. First is clear, valence band and conduction band. Or we should take another empty slide. Okay, so y is K, y is E. What is significance of K? E is the energy states of band gap. K is a propagation wave vector. It is decide the direction of the wave motion. Propagation wave vector, known as propagation wave vector. So let's say you have two materials. Let me take another. Electron is if excite from the conduction band. Sorry, this is valence. So EC, EV, this is EC. See, two picture are there, one this and another this, 1 and 2 picture. One is corresponding to the direct band gap, this is indirect. See first the pictures. Okay, electron is from valence band to transit upon incident of photons. If incident photon should be greater than this gap, this is known as the band gap of the semiconductor. Only one electron can excite from conduction band or equal to maybe valence band to conduction band. So this is k vector, also related to the momentum. Here is the k is not changes, only one position, electron goes up and down. If come back, emit the photon again. So during the transition there is no change in k, delta k should be 0. No momentum change, should not be the momentum change. While in indirect band gap semiconductor, electron first goes up, then via phonon. This is for two process are, when the electron goes like up and goes like that, or reverse, when return it come back. So when return it, this is phonon conversion from a to same energy levels, phonon conversion, then energy goes down. So here is k not equal to 0. This is not for the same k value, this is k1 and this is k2, there are the difference, but this is initially and coming back only the same position k. Got it? So in direct band gap and direct band gap, direct momentum changes should be 0, momentum should not change. Okay, and indirect band gap semiconductor, momentum will change via phonon conversion. So this is known as non-radiative. Do you know radiative and non-radiative? So now come to the question. Okay, I will explain radiative and non-radiative. First, see the question. In indirect band gap semiconductor, a transition between conduction band and valence band result in. Also, you can see the change in energy. This is y-axis in energy, x-axis in momentum k. Now, please try to analyze these options. Which option will be correct according to these diagrams? Others, please try to analyze these pictures and give your whatever you learn from here. Please try to give your answer. Okay, nice. Yes, please. Is both energy and momentum. Somebody ask something, ask. Yes, please, you can ask.
By analyzing these,
Yes.
by analyzing these diagrams,
Mm-hmm.
change in both energy and potential is my
Mm-hmm.
answer, sir.
Yes, sir. Okay, okay, thank you. You can write in chat box. Okay, will be better. If have any doubt you want to, you can also write in chat box, or if not explain, not able to get me and you, then you will unmute and please ask. Okay, so see multiple choice option.
Hello,
Yes,
good evening, sir.
good evening.
So I wanted to ask that
Hmm.
why are we having x-axis momentum?
Okay.
How is it coordinating with us to get direct bandwidth? I'm understanding why it is direct, why it is not indirect bandwidth due to the energy loss of momentum loss.
Hmm.
Why exactly momentum we are considering here?
Okay, so do you know how wave propagate? So
It's a longitudinal waves and
so we will deal the transition or momentum any electron and photons via the motion of these particles. Motion of these particles are related to the wave vector k. So we will detect the motion. How is this going from here to here? How we can check where is the electron goes? If you want to move from one place to another place, want to know coordinates and direction, so like that in the analogous we also detect the how the electron is going from one place to another place in the semiconductor, from valence band to conduction band, which direction also represented by the wave vector k. Motion, dealing of the motion of the electron, which direction, and how the propagation of particle, photon or electron related to the wave vector k. Let me give me more to you. See, in quantum mechanics we will deal these motion in quantum mechanics. EM waves, let's say you have these are the perpendicular on the each other, and motion of these, let's say, in this direction perpendicular to the vibration of these planes E and K. These are EM waves, let's say. So direction of these EM wave decided by these. This is the physical significance of K. So we check the k first. Where is the particle or photon goes and which direction? So this k give to you feel idea of the direction and the motion.
Got
Okay.
it, sir.
Okay, thank you. So in quantum mechanics point of view, every particle, electron or anything are associated the wave.
So we can say that the E versus K plots can be different for different semiconductor materials also.
Yes, difference. So okay, so, so many concepts are there. So heavy and bands also decide that these are the radius of curvature. See, these are two type of radius of curvature. So effective mass also come into the picture. What is the effective mass of the electron and holes? So shape of these bands also give the idea. So direct only k, please remember this, delta k should be 0 direct, and energy also changes. This is E on the axis, energy and k, while in indirect both are changed. First this is k, change in k, this is indirect. Okay. What is the non-radiative and radiative recombination? Anyone?
I think in the radiative one, there is some loss of energy in the form of heat. The electron goes from one state to another separate state, and then it comes to the ground state. And in the non-radiative one, it directly goes from the excited state to ground state without additional loss of energy.
Think, let's say, okay, partially correct, partially. When electron come back from higher energy state to lower energy states, these are the energy states. Or you can say in the semiconductor context, from conduction band to valence band, directly come without change the k, transition from upper level to lower level, it emits the photon, which is energy h nu corresponding to this gap. If goes down, photon is emitted and energy, this is, let's say, easy. This is the total conversion of energy in photons, which is known as radiative. Radiative means we will detect these photons in like PL, photoluminescence, in the form of the luminescence, and we can detect by this is technique known as PL, photoluminescence, or other detector. If we put the detector which detect the photons, we will count. But in non-radiative, such let's say this is phonon conversion, phonon, not photon. Photon is transition. This is change only in the K. This is phonon, and after this photon emits the photons. So this is phonon conversion known as non-radiative. Why non-radiative? We can't detect these. This is, let's say, we have material and have atoms. Vibration of these atoms, energy loss, let's say energy is absorbed and lost by the vibration and heating the material, but not luminescent the photons, known as non-radiative. So we can't detect, we will not see any luminescence. This is known as non-radiative. Okay, clear now? Thank you. So please see the definition and picture. So let's move next question. The nature of the variation of momentum P and wave vector K in the electronic free space is these are the options: linear, parabolic, hyperbolic, circular. What will be the answer? Okay, see. P equal to h cut k. This is the formula for a free electron in free space. And energy p square by 2m, which is known as kinetic energy, or in say h cut square k square by 2m. Now please try to, let's say, ask into for photon, for momentum, and for energy. What is the dependency of the K? For momentum and K, you can see this is constant, h cut is constant, Planck constant, sorry, and these are the wave. So these are the vectors, but energy not the vector. Energy is scalar, momentum is vector. So this is just power 1 linear variation. Momentum is linear variation. For energy, what is the ek variation? Yes, please. Okay, see this formula, parabola. If y equal to 4ax square, this is equation known as parabola, parabolic. So E and K square known as parabolic relation. That's why I am draw these parabola EK diagram, energy versus K, conduction band and valence band for free electron. Okay, just wait a minute. So answer, let me check. Read this question. I will discuss the other nature of, let's, hyperbola. People are asking hyperbola nature of these. Please see this question other. Okay, let me admit. Okay, so on the y-axis these are the parabola, but let's say I am drawing like these are the hyperbola, pollic nature, and equation of these x square upon b square 1, these eccentricity and things are add a comma 0, this is minus a comma 0. Nature of these, yes please, next question. Okay, my camera is not on. What will be the effective mass of electron if the radius of curvature is increased up to two time? Do you know formula about the effective mass of electron? Anyone?
Hello.
Yes, please.
It was something along the lines, I think, m naught divided by 1 minus root a square by c square root over or something like this, I think.
Effective mass.
Either it is effective mass or maybe it
E
is
and
rest
K.
mass.
Differentiation between E and K. Like that. Think about the differentiation of the K with respect to K of E. mass and curvature are inversely proportional to. Okay, so effective mass represented by m star, which is h cut square, and double derivative of E with respect to k inverse. This is the formula with k square, sorry. Now what is the question? What will be the effective mass of the electron if the radius of curvature is increased up to 2 times? This is give to you radius of curvature. Okay, so if radius of curvature is twice up to 2 times, then effective mass will be 2 times. Clear? Let me ask the question like that. This is one curvature and this is another curvature, green and red. This is, let's say, 1, this is 2. Which one has more radius of curvature, 1 or 2? This is let's say R1, this is R2. So R1 and R2. Bigger sphere means the radius of curvature is higher. So effective mass of which one is higher, 1 or 2? Will be higher for 2. Okay, so curvature means how, let's fit the sphere. This is known as radius of curvature, and air will be bigger sphere for the 2. Radius of curvature will be more. Am I correct or something has miss? Anyone has any doubt? Okay, let's move forward for next question. Yes, in a intrinsic semiconductor such as silicon, the movability of the electron in the conduction band is greater than the movability of the holes in the valence band due to movability is inversely proportional to the effective mass. Now please try to give the your options. Which option will be correct according to you? Okay. The movability of the electrons in the conduction band is greater movability of the holes in the valence band. Hole has higher effective mass is greater than, that's why movability is low of the holes as compared to electron. That's why we prefer n type, because electron move faster, movability of electron is faster, higher than the holes. Next question, please see. For a intrinsic semiconductor with a band gap of 1.5 eV electron volts, what is the position of the EF? EF is a Fermi level at 300 Kelvin if effective mass are given to you. Yes, please. Let me give to you formula. This is the answer, but this is the formula. Please try to now solve. You have formula. EF is a Fermi level, which is Eg, band gap of the semiconductor by 2 plus 3 by 2, 3 by 4, kT ln mass of holes divided by mass of electrons.
Sir,
Yes, please. KT value at 300.
sir, I wanted to tell that since it is an intrinsic semiconductor, then we roughly assume that the window will be like half the band.
Your voice is not clear to me. Please write what you want to say. First, please try with this equation. You have formula Fermi level 4. Put the value and solve. You can use the calculator. Please solve this equation. Okay, since it is an intrinsic semiconductor, can we roughly estimate the value of EF with the band gap of the band gap, since the options are different? Yes, we can choose. This is number. Let's see. First, try with this number. I will come to your point. KT will be 0.025 at Ln. This is mass of hole, is 5 times of mass of electron. This is ln 5, value of ln 5. Let me use the calculator. 5 is 1.6 multiplied by 0.025 MeV. This is in electron volts, and multiply by 0.75. This number is around 0.0301. So this number is very, you can see this number is very less with respect to the band gap. Please put this number 1.5 by 2. This is around, okay, this number is around 0.7. This is half. So, and adding on this number, you will, so try to see which option is correct. Only just half of the band gap near, but in the numerical we can't, if fundamentally is right, you fundamentally is indirect band gap semiconductor, this number should be very less. So just we can solve easy by 2, but the number provided by in numerical may be different, may be higher. They didn't think about the fundamental, maybe put the higher numbers. So please solve. Okay, you will get definitely around this number after solve. Okay, around 0.78 EV. Next question. In an indirect band gap semiconductor, a transition of an electron from conduction band minimum to valence band maxima primarily result in emission of photon only, emission of the phonon only, no energy release, simultaneously involve of the photon and phonon. So we have already discussed this. Please give me the answer very fast. We have already seen na indirect band gap. Yes, you are. I think all are known this now answer. See, no doubt. So let's move the for next question.
Sir,
Yes.
the fundamental questions I wanted to ask that, sir, why the mobility of holes? That question. Why is there a difference like that? Why the electron mobility is higher? You said.
So the nature of the electron has negative effective mass, and if we find the by the curvature, so it is the effective mass is the concept for the, you have to think about the effective mass, where is the coming, what is the parameter which is associated with the effective mass. This is
I think it's interaction between the various ion cores.
yes. So interaction, so hole, you will find the more effective mass for holes, that's why mobility is inversely proportional to formula. You can find the mobility relation between mass and mobility. So interaction will come the point for the electron and holes effective mass. This is when we include the all forces by the electron and electron nucleus and all these things in quantum mechanics. We will deal these effective mass in quantum mechanics. Okay, see this question. The requirement of phonon during the band to band recombination in indirect band gap semiconductor arise due to the conversion of and see this is indirect. Please fast. Energy only, momentum only, charge only, both energy and momentum. Transition from air to air. This is for indirect. This is valence, this is conduction. Energy of this is. So first during the transition phonon, then photon. And energy, this is E and this is K. K also changes from air to air. This is change in K. Both energy and momentum will change, na? Agree? No doubt. Let's move for next question. Which of the following material has least suitable for light emitting diodes due to its band structure? These are the materials: gallium arsenide, indium phosphide, silicon, gallium nitride. Light emitting diodes. We want two fluorescent light emitting diodes during the transition. This is the electron come from upper level to down level, photon is released based on this concept LED. Fluorescent. So which type material should be suitable for direct or indirect band gap? Tell me, direct or indirect? Phonon doesn't give you the fluorescent. All are there. Don't give this answer first. Please give me the answer this first. Direct or indirect LED? Which material do you will take if you will design the LED? You have two materials: direct band gap materials, indirect band gap materials. Which LED material? Okay, nice. Direct, because we want two photons. So least suitable. See, least suitable. Indirect also give, but not preferred, not suitable. So which material is indirect? Question is like that: which material is indirect? Now please, do you have idea about silicon? Silicon is direct band gap material or indirect band gap material? No, silicon is indirect. Okay, thank you for indirect. So now please give me the answer fast. Silicon is indirect here. And other are direct. So option will be C. Clear this question? Let's move if you have no doubt any. We have so many questions. We have to solve 18 question. What will be the probability of the finding electron in a state? You have the state, Fermi levels, you have the position at this is the at the conduction level. The probability of the finding of the electrons, let me write the formula, E minus EF upon KT. This is the formula. Probability of the electron find any state given in any states. This is the energy is state, electronic states. Electron are present. Sorry. Energy where electron are present. EF is the Fermi levels. K is a constant, Boltzmann constant, T is the temperature. Please write this formula and then let me solve with you. Please also solve you. And this is the formula. And E is also given to you, EC plus 3 KT. And EF is also given EC. Now please put the value in this exponential. This is EC plus 3 KT minus EC. EC also cancel out, 3 KT, KT also out, 1 upon 1 plus exponential 3. Please solve this. You can use calculator. It will give to you 0.47 around this number. Please check your answer with me. Clear? Any doubt? Let's move forward. Next question. Where would be the Fermi level located when the probability of the being state field at EC plus KT is equal to the 1/3 probability of state is empty? So you know the probability of the finding the electron. We have already discussed E minus EC upon KT EF. For empty, you know the sum of the probability finding and not finding will be 1. So this is for field and we want to empty. empty. Let's say probability of this is field F, this is empty, 1 minus field. Sorry. So 1 plus exponential, this is the term, this term. After solving this, exponential above and 1 plus exponential below. Let's say this is x for easy. So according to the question, what is the question? 1/3. When the probability of state being filled at this is the state is equal to the 1/3 of the state are same. So this is 1 minute. Probability of field, this is a 1/3 of the equal to the 1/3 of the please use this relation now. You have empty and you have filled. These are the expression. So what is the filled? 1/3 of the empty, and filled, you know, 1/1 plus exponential. Let me put x just for, and this is, we have already solved, this is okay, where x is what is x? E minus ef upon kt. Now try to solve this. What will be the next step? This is 3 and this is cancel out when we multiply 3 exponential x. Am I correct? So what is the exponential x? Let's put e minus ef upon kt. Please check the log 3 or ln. This is log e minus ef upon kt. Now multiply e minus ef kt ln 3. You have to find ef, and what will be the, so e minus kt ln 3, and e have already, you have given ec plus kt. Put this value, ac plus kt and minus kt. This will be the answer. So okay, sorry for this is the answer, this is incorrect. Clear? You have to remember, let me please remember this formula for finding the of electron in state E. Energy of state E will be 1 upon 1 plus exponential E minus EF upon KT. Please remember this formula. And not finding, or empty, this is 1 minus finding. This is the concept, and according to the question you will able to solve. Whatever the question given, E will give to you, and the condition between finding and not finding will give. Then you can easily find the where is the Fermi level. This will be given to you in relation between the finding and not finding. Clear? Let's move for next question. What will be the electron concentration in the piece of the silicon sample maintained at 300 Kelvin with a whole concentration 10 to the power 8 per centimeter cube under equilibrium condition? Intrinsic area concentration also you give. Whole electron concentration, you have to find the concentration of so you know Ni square equal to number of electron and holes for intrinsic semiconductor or other type semiconductors at equilibrium. Under equilibrium condition, so you have 10 to the power 10 per centimeter cube, and other holes concentration means P, you have P 10 to the power 8 per centimeter cube. Now you have to find N. Please put this in this formula, 10 to the power 10, this is square, N is you have to find 10 to the power 8, this will be 20 divided by 10 to the power 8. What will you get per centimeter cube? Clear? Should I move forward for next question? Please respond, or are you still solving this question? Okay, thank you for your response. Let me project next question. Intrinsic carrier concentration of the semiconductor increased from 10 to the power 10 per centimeter cube to 14 upon increasing the temperature from 300 to T1. The band gap of the material is also given to you. The value of T1 is close to. Oh, sorry, question is not. Now this is the question. Please use this concept. This is the formula. Or you can put just a constant for this exponential is by 2 and concentration from here to here upon increasing the temperature. So let me put, this is for A, this is for B, this is A exponential, this is constant A, Ag upon 2 kT. Let me put 2 kT A for concentration of B, two kT B. This is equation first, this is second. This is the formula, please remember this. Now please divide these 1 and 2. What will you get? A cancel out. This is exponential Hg by 2 kTA. This is 2 kTB. N upon NB. Can I, this is exponential e to the power x, let's say this is x, so this, and divide by x y. So you can you write, if you have same number, so according to this we can Ag by 2 kTA minus Ag 2 kB exponential. You can take common Ag by 2k. You will get just TA minus TB. You can take the log ln this is band gap. Now please put the numbers. You have A and B according to the temperature. TA equal to 300, TB equal to T1, and Na equal to 10 to the power 10 per centimeter cube, and B equal to 10 to the power 14. Sorry, let me write down below. To the power 10. Please put this number in below this equation. This is 14 per centimeter cube. Please try to solve now. What do you have? ln you have the final formula this, and Na equal to 10 to the power 10 and B equal to 10 to the power 14 per centimeter cube concentration. According to the temperature, T1 is 300 K and this is T1, and band gap also you have 1.1 AV, I think. Yes, these are the given parameter. Put in this equation. What is 10 to the power 10, 10 to the power 14 Ag. Let me put the value of Ag. I will put this is in later. 300 Kelvin, and this is 1 upon T1. This is ln to the power minus 4. You can put the value of K and Eg, then only the T1 is remaining here, nothing else. Now please try to solve. Or just T1 minus 300 Kelvin, 300 T1. KBT at T equal to 300, this number will be 0.025 in electron volt. So let me, this is easy. Now put Ag, band gap 1.1 AV, and leave this is 2 into sorry K into 300, and T1 leave as it is minus 300, and put this value, this number K into KB Boltzmann. This is the number 258 or 26. You can put 258 or around 26. And AV 2 is 0.0258 in EV. EV cancel out, and this number is, what is the 10 to the power minus 4 log ln? minus 4 into ln 10, so multiply by 4, this number will be 9.210, this number. Now you have only t1 as the variable here. Please solve these numbers. Where is sorry, let me solve for you. Minus 9.210 and 1.1 divided by 2, 0.0258 with the t1. Can we take minus here, the common 300 minus t1. Okay, these minus cancel out. Now multiply this number by this, 9.21 multiply by 2 multiply by 0.0258, and this number will be 0.475 t1 with 300 minus t1 plus 1. Next will be just 1 minute. This will be total summation of this and this, left side 475 t1 equal to 300 divided by 1.475. What will you get? 203.38 around. I have missed the sum. No, this is the same. Okay, so concept, you should remember the concept and follow the calculation. You will get the answer here. Next question, let's see. If the electronic mobility of the semiconductor is 600 centimeter square per volt per second, then the carrier scattering time is estimated as. Let me give to you formula. Please use this formula and check your answer. You have 2 minutes for this. Please solve, everyone. E is the electronic charge in coulomb, 9.125 minus 31 kg. You have to find the carrier scattering time. movability also given. So use this equation. This is in, please check the units also. This is in centimeter square volt per second, and right side, first convert this number into SI unit, standard unit. Centimeter will, please convert centimeter square into meter square. Then right side put the number in this you have given and solve for the scattering time. Are you able to get this answer in second? Let me convert for you. 1 centimeter equal to, or please use this 100 centimeter, or into, so 1 centimeter square equal to 10 to the power minus 4 meter. Please add this number, 600 into 10 to the power minus 4 meter square in place of centimeter square. Volt inverse, centimeter inverse. So now you have 600 into 10 to the power 4. Right side you have 2, charge of electron, charge m, and mass of electron. You have to put this number. So 6 into 10 to the power minus 4, charge of electron minus 19. You have to find mass of electron, kg. This is in coulomb. All are in SI unit, so time will automatically come in second. You have to find out tau. 9.1 10 to the power minus 31 into 600, 1.2 minus 19. Now please solve this equation. Use calculator. Please check your answer. Let me also do exercise for you. 9.1 multiplied by 600 divided by 1.6. This is 3412.5 and 2 number 10 to the power 35 and plus 19. This will be plus 16 minus 16. Okay, so please convert into the respectively units. Let me put this number here, scientific conversion. So around 10 to the power plus 3 minus 13 is left. This in second. Any doubt? Here is the question. First convert, if right side is SI unit, left side should be the SI unit. When you solve the question, please check the units also. Okay, let's move for next question. If the resistivity of the intrinsic semiconductor is 8 ohm per meter at 300 Kelvin, now it is increase the temperature up to 600 Kelvin. Then the resistivity 2 ohm per meter, the energy band gap in electron volt. These are the options. Do you know formula? A exponential Ag by 2 kBt. So conductivity is directly proportional to the concentration. This is directly proportional to, and resistivity is inversely proportional to the conductivity. So ultimate rho will, this will be the number, this will be the number. So exponential minus Ag by 2 kT. Okay, this will be the expression. Please use this expression for rho 1 and rho 2. Let's say this is rho 1, increase up to this is rho 2 according to the temperature T1 and T2. So rho 1 upon rho 2 exponential, material band gap will not change, will be the same, T1 upon upon Ag upon 2 k T2. Please further solve this. Just exponential Ag upon 2 k, please take common, minus T1, this will be 1 upon T2. So this is the expression. Now please put the value and check your answer. Okay, let me use this final expression you have. Also ln kT. Okay, please use this expression. Put the number and find the energy band gap. Easy. You have to find just easy. What is T1? Let's say this is rho 1, then this is T1. This is rho 2, T2. 300 Kelvin, this is 600 Kelvin. This is rho 1 is 8, this is 2 ln T1. What will be? This is 300 and this is 600. Now you have to and put the value of K in electron volt. This will be 8.6 around. Let me check the number exact. 10 to the power minus 5 electron volt per. Please put these number in this equation and check your answer. You can take 1 or 2 minutes. Use calculator. Please try to solve. You can solve. Please keep it as a homework and try to solve. You will get definitely 0.36. Let's discuss next question. A semiconductor material has an intrinsic carrier concentration. This is 2 into 10 to the power 16 per meter cube. The electron and hole mobility, these are the numbers 0.14 and 0.06. The resistivity, here is a rho. What is the rho? Movabilities, electron and holes are given. So you know the mu n I into charge E. For electron, this is electron hole, let me put P, number of hole P, and the charge of hole will be, this will be electronic charge negative and positive. You have to put just number. So, and resistivity inversely proportional to the conductivity. This is for conductivity. This is the relation for resistivity in conductivity. One minute. So let me just put conductivity. Number of holes and electrons are not the same. Intrinsic carrier concentration, electron or mobility also given. So intrinsic means number of electron and holes are equal. So mu of hole and mu of electron into charge. So first you have to calculate. Please calculate this number. What is the intrinsic carrier concentration per centimeter cube, and hole and electron, these are the movabilities, and E is the electronic charge. This is the 1.19 coulomb. First calculate the conductivity. These are in all in SI units. Solve this equation, these numbers. Let me calculate with you. Do me 1.6, this number 3.2 10 to the power minus 3, and this is 0.14 and 0.06 multiplied by 0.32. This will be no 0.20 to conduct, then this will be the number. Now resistivity, you have to put this number in reciprocal. 1/64 into 10 to the power minus 3 will be 1000. Did we do some mistake? Please check your answers. Let me show you the solution. What we have got. Concept is same as we discussed. This is conductivity, and conductivity is 1 upon rho resistivity, or vice versa. So this is, I have changed the numerical value. Please check your answer. This will be maybe should become this number. Okay, so just you have to use this formula and do the exercise with number. Next question, at very high temperature the position of the Fermi level in p-type semiconductor shift to. At very high temperature the position of the Fermi level, what will happen when the temperature increases? P-type or N-type, you can take both type. If we increase the temperature very high, so answer when we increase the temperature, bonds are breaks and electron hole concentration increase. If the electronic concentration is high in the conduction band, valence, the Fermi level will shift to the conduction band. So see the explanation. At very high temperature, intrinsic carrier concentration increase significantly due to the thermal excitation and making the behavior of the semiconductor more intrinsic rather than the extrinsic. In p-type semiconductor, the Fermi level, which is initially lie closer to the valence band, move toward the Fermi level to the middle of the conduction band. So p-type or n-type semiconductor are going to the intrinsic type, pure purely pure semiconductor, rather than the N and P. Bond are broken and due to the thermal excitation, and be aware of these N or P type semiconductor still not now no longer still exist. Yes, downward at very high temperature. Let's say N type, you know, Fermi level goes up. For P type, closer to the valence band. This is conduction band, this is valence band. This is P type material, this is N type. At upon very high temperature, high temperature, when we give this, please see the explanation. Intrinsic carrier concentration increasing significantly rather than the doping. So these goes around the come closer to the mid gap. It means number of electrons and holes again will same in the conduction band and valence band. Pure means concentration in P side and side will same of the N and P. That's why Fermi level will lie in the middle of the band gap. Next question for you. Which of the following are true for the intrinsic semiconductor? N and P are the electron and hole carrier concentration, and Ni is the intrinsic semiconductor concentration, carrier concentration. Extrinsic semiconductor. We have already seen intrinsic. We have already discussed the question N into dou. For extrinsic, you have to find for extrinsic. Will be same and will exist. C will be the answer. For this is at the equilibrium position. Only for valid for, please remember this, only valid for the equilibrium point. If we disturb the equilibrium point, this product of these N and P number concentration, N side and P side, will not be the same. Like solar cell, we have incident the photons. Then what will happen? Number of charge carriers is N side and P side bond are break or in space charge limit or depletion region. You know, let's say this is space charge limited region. This is P and N. When we incident photons, electron hole pair are excitons of electron hole pair are generated separate and carrier concentration goes up. So this number will not same Means if you give the extra energy or something else, it means you disturb the equilibrium point. When equilibrium point is disturbed, number of charge carrier are not the product are equal, for solar cell will be the greater. Okay, next question. The monthly average, this question is related to the first assignment. Let's discuss again. The monthly average of the daily extraterrestrial radiation falling on the horizontal surface, this is the 45000 45,000 kg per meter cube day, and the ratio of the monthly average of the sunshine hours per day in monthly average maximum possible sunshine hour is 0.51. The empirical constant and we are given the monthly average daily global radiation in kilojoule would be. Okay, let me please see, this is the solution and this is the Hg. H naught is the total and these are the empirical constant S by S max, and you have H naught, this is H naught, and do you have A and B, these are the empirical respectively, the empirical constant, monthly average daily global radiation and what else, and the ratio, you have already a ratio S by S max 0.51. just put the number in this expression you will get the exact value. Please see the solution of this expression. Okay, so I think okay, so this is all about for today. So sorry for the assignment purpose because we have restrictions, we can't discuss these recent means current assignment. We can't provide you the solution, only I will give the explanation and concepts. Option may be okay, but the option is not there. You can do the mail respectively team or TA regarding the correction in the option. If your calculation is correct according like that, your answer will be correct. So some error may be in the during the typing. Just follow the concept.
Hello.
Yes.
Yes, sir. So I wanted to ask in the first week section, there
Mm-hmm.
are a lot of formulas he gave around at the end of the, those solar radiation and stuff.
Mm-hmm. So
List or certain formulas are necessary.
you have to remember, means you have to physically interpolate. First you have to learn, na? Basic thing is the, please analyze these, what is the angles. In first assignments all are the angles. Slide 6 and 7 ones. Okay, let me come to the, yes please. What is your query? 6. In an indirect band gap semiconductor, transition with electron from the conduction band to minimum to the valence band maximum primarily is result. Yes, I will upload this PPT, and also I have already uploaded for first. Let me give to you the link. 1 minute. This is the link regarding the material and PPT and recorded lecture. You will find all session assignment first, second, third, fourth, fifth, 8. I will upload here.
Hello, sir.
Yes.
Sir, if you don't mind,
Yes, yes,
I
yes.
wanted to ask, sir, that you look familiar. Like, did you do another TA session for something related to Assis sir's nature and properties of material course or something in NPTEL?
uh, this session, no, no, I am only for, earlier I was there, but currently only for photos.
Years back, 1 or 2 years back.
What?
Maybe 1 or 2 years back.
Yes, yes, I was there last year there.
Okay, okay. That I did it. That's why I remember.
Hmm, I see. Oh, so Shruti, what is your question in slide 6 and 7? This is the 6, answer is C, and this is the 7. Shruti, are you there? Please check your answer and query. Okay. So what you want? Okay, okay, thank you. Good result. So almost 2 hours is completed. Is also, we have only 2 hours for this session. If you have any query or any doubt, you can email me, and my email, please note, this is my email, harishankar_s@ph.iitr.ac.in. I will upload today after the session. Okay. So let's thank you all of you for actively participants, and we will meet again next Monday with third assignment. Thanks to all of you. Okay, let me close the session. Thanks.